9.3 is linear differential equations. So we've got another form of how a differential equation could take, and we'll learn the method to solve. This is the second and last style of differential equation we will learn about. And this is a fun one. So I really enjoy differential equations and solving them, as you can tell. So here we go. A linear differential equation takes this form: y prime plus f of xy equals g of x. So we've got some function of x there and some other function of x here, a y prime and a y there. So let me show you some examples that we will end up solving later this section. So how about a really simple one: y prime plus 2xy equals x. So there's my f of x and there's my g of x. Right? It takes this form. Okay. Oh, I guess that's the only example I'm going to show you. I thought I had another one. So we'll end up solving this a little bit later. I think we do this one and one other. So what's the technique to solve? How are we going to solve? This seems really strange at first, but maybe, hopefully it'll come together. We're going to multiply both sides by this. E raised to the integral of f of x dx. So whatever function we have there for f of x, we're going to take that. We're not going to take the y with it. We're just going to take the function. We're going to take the antiderivative of that, and we're going to put it into the power of e. Now, whoever thought of this technique is a genius. This is a brilliant way to begin. Okay, so we're going to find that, and then we're going to multiply it to the left side and the right side. Okay? So what is that going to leave us with? Oh, sorry. Going too fast. This thing, it has a special name if you refer to it. It's called the integrating factor. Maybe it'll make sense why that name is what it is, but okay, that's the integrating factor. When you're doing your homework, they're probably going to refer to it as capital I of x, this whole thing here. Capital I of x. I don't think that's necessary. I don't like to do that. It's not uncommon when you learn this to call it capital I of x, but I think that overcomplicates things. Let's just call it what it is, e to the integral f of x dx. It's the integrating factor. All right. But when you see it in your homework, don't be surprised. Hey, what does I of x equal? I don't know. They may or may not actually use the language integrating factor. They might just call it by that. Okay, so what happens when we multiply both sides by this? So we're going to get, and this is there's a lot going on here, so I'll give you a moment to copy this. But right, we've got the e to the integral f of x dx multiplying by y prime. Multiplying here, it's pretty common to put it in the middle of f of x times y, but it multiplies by that term as well. We like to put it in the center. I'll show you why in a moment. And then we're going to multiply it to the right side as well. So g of x times that integrating factor. Okay, what the heck is this? What is going on? Who thought of this integrating factor? This is a mess. Here's why. Look very carefully at the left side. It turns out this is the result of a product rule. Like what? This is the result of a product rule? Yeah, it's got two terms. Okay. It's got y prime here. It's got the original y there. It's got e to the antiderivative f of x dx, and it's got the e to that antiderivative times f of x. The derivative of e to the integral f of x dx is f of x e to the integral f of x dx. And then we got the y prime and the y. I'll show you the next step. All of that is the product rule applied to this. If you were to perform the product rule on e to the antiderivative f of x dx times y, you would get exactly that left side. That is genius. Okay, when we actually do examples, it's going to be a lot more clear that this left side is the product rule of our next step. When we have the e to the antiderivative, it might be lost to several of you. You know, we can see the y, right? We can see the y prime in the original, but the other part maybe not. When we actually have these integrating factors worked out with actual functions, hopefully that'll be a lot more clear. But every time we solve one of these, after we multiply, it's always the result of a product rule. So it's like we're working backwards. Take the derivative of that, the integrating factor times y. Now at this moment, the right side we're just going to keep. So that's equivalent. That just gets copied. What do we do then? Since we're taking a derivative here, what cancels out a derivative? Well, an antiderivative, obviously. So at that moment, after this step, we would integrate both sides. So that would cancel out this derivative. We would need the integral of this whole thing. So that would leave us on the left with just these two things multiplied. We're going to integrate both sides, and then we're going to isolate y. What's really nice about linear differential equations, we can always get an explicit solution. We can always solve for y. Okay, so this is all pretty abstract. We got all these functions flying all over the place. Let's see an example, and we're going to start off with the one I mentioned just a moment ago. I like to whet your appetite that way. Let's find the general solution. Okay, y prime plus 2xy equals x. So we can tell this is f of x. This is g of x. Now what's really important to us at the beginning is the f of x, right? Because we're going to start off by finding the integrating factor. And I've kind of shown you how it plays out. Well, it's really not that difficult here. We take 2x. We want e raised to the integral 2x dx. So we put the 2x in right there. Well, that integral is x squared. Okay, so our integrating factor is e to the x squared. Notice that we do not want to say x squared plus c. We do not add the c in this step. We just say e to the x squared. And if you would like to know why we don't need to add the c, there's a pretty simple reason for it, but I don't want to get into the explanation. It's simple, but it's not immediate. It's not necessarily super fast. So there's all these kind of weird things happening with the c in this chapter, right? And this is no different. So when you do that integrating factor, don't add the c. It's just x squared. Okay, so in your homework, I haven't looked at it carefully yet, but just the way they're phrasing it in the textbook, that's I of x. So if they're asking you what I of x is, okay, that's the integrating factor, right? We got it. So what's the next step? Well, if you wrote all that down, we're going to take our integrating factor and we're going to multiply it to each of our three terms. So we're going to say e to the x squared y prime plus 2x e to the x squared y equals x e to the x squared. Again, in this middle term, I like to put the integrating factor right there in the middle. There's a reason for that. Why do we put it right there in the middle? Because what is this left side the result of? It's the result of a product rule on e to the x squared times y. Now maybe it's easier to see this. If we were to perform the product rule, well, I might copy it and then multiply by derivative of y. Then I'll take the y, but then I'll multiply it by the derivative of this. There's a chain rule, right? Okay. Hopefully that's a lot easier to see, that reverse product rule happening. At the end of the day, though, really all you need to remember is when you do the reverse product rule, it's always the product of your integrating factor and y. Always. Your integrating factor times y. You're not going to have to think through, oh, what would this have been in a reverse product rule? What would be the product rule to give me that? It's always your integrating factor and your y. Boom. At this point, the right side needs to stay the same. We haven't actually done anything to both sides. We've just rewritten this, so we need to copy that. Okay, what comes next? We integrate both sides. Now I'm really showing you all of the steps here on the left. When we integrate, of course, it's just going to cancel out the derivative, but we integrate that with respect to x. So all of this is going to cancel. But we do, of course, have the integral on the right side. So I'm going to rewrite it this way. E to the x squared times y equals the integral of x e to the x squared dx. Okay, now this is really looking good. If I can simply find this antiderivative, then I'll be like one step away. If I can get that, man, I'm knocking at the door. What should we do to find this antiderivative? What technique? If we were in class, I'd give you a moment. But since I'm not talking to you right now, I'm sitting here by myself on my front porch. I'm just going to tell myself that I want a u sub. Let's just show it all. I'm going to take u to be x squared. So I got my du, and I want to divide that 2 on over. We've done this, I can't even count how many times now. So I'm going to copy my left side over and rewrite this integral as 1/2 integral e to the u du. Which of course will lead me to a 1/2 e to the u plus c. And I'll put my u back in. Oh, okay, that's the end of my page here. I got my left side still, putting my u back in. Okay, 1/2 e to the x squared plus c. Looking really, really good. Technically, this is an implicit solution, but there's no reason to stop at this implicit solution when all I need to do to find an explicit solution is divide by my integrating factor. So I'm going to divide this on over here. That's the beginning of my next page. Now I suppose you could write it this way. I need to divide the entire right side, including the c. Don't leave the c just hanging out over here. It gets divided by e to the x squared as well. So I might say y equals 1/2 e to the x squared plus c all over e to the x squared. Well, that would be okay, but there's a better way to do this. If I divide each one of these individually by e to the x squared, it looks really clean. 1/2 plus c, and hey, let's call this e to the negative x squared when the c divides by it. Now that looks really, really good. We like simple looking solutions, explicit solutions that have been cleaned up as much as we can are preferred. All right, well that was a lot of fun. I've got one more example here in 9.3 in the next video.